Hi, my name is Sarah Mertz, and here's my micro project for lectures 09 and 10. So for collision detection for array and an edge AB, we're going to use array as CD. You need to see if they intersect. So if AB det AC is opposite of AB det AD, and CD det CA is opposite of CD det CB, then that means that C and D are on the opposite sides of A and B, and therefore it intersects. So you also need to make sure that C and D are inside the bounds of AB. So to do that, for C, you would take the dot product of AC and AB and make sure it's opposite of the dot product of BC and AB. And that way you know that they're pointing towards each other. So C has to be in the bounds of AB, like you can see on the left. If they both point the same direction, if the dots are both equal to each other, the signs are, then it's bad, like on the right, and they're pointed the same way and it's outside the bounds of AB. To select the edge of the polygon that R intersects first, you travel along the array with a certain time t, checking at each new t to see if it intersects with any of the edges of P. So I iterated through my edges and did the collision detection. And then when it intersects, you compute the new direction of it and follow the new vector. To compute the corresponding collision point for x, so for every distance that your particle moves or your ray moves, because it will have an ending point, you compute if it intersects or not, if it fails the collision test, and if it does, that is the point at which it intersects. To compute the direction of the reflected portion of the ray, we'll just start with what we have. We have I, which is your incoming vector, and then you also have your normal of AB. So you can see that the dot of I and N scaled by N is, you can see that down by where A is, but then you can also see that I is just vectors so that you can move it, and you see that where it's also I. So you end up figuring out that if you subtract the dot of IN scaled by N twice, then you get your R, which is your reflected ray. Your overall algorithm for tracing the path is basically what I just described. Every time you move, you detect if you collided or not. Every time you move, you subtract the distance from the total distance that you have, so you know how far left you have to go. You compute your new direction if you did collide, and you go along the new vector, and you continue the ray along the new path as long as your distance does not equal 0, and you repeat the algorithm as long as your distance does not equal 0. So to produce an animation of the particle moving inside of the polygon, which is what I did, you basically do the same thing but just with the particle, and you don't keep track of where you've gone so much as where you are and where you're going. So you move the particle along the ray with your velocity, and then every time I made my particle more like, I would calculate the next place it was going to go, and that was the ray that I was using, and then you continually recalculate where it's going to go, and then when it hits an edge, then you switch your vector that you're moving along. And now for my animation of the particle inside the polygon.